We have been told that the history of human civilization is the history of energy. From the discovery of fire to the taming of the steam engine and the splitting of the atom, every major leap in our species' development has been defined by our ability to capture and manipulate power. But today, we are hitting a physical limit. We are still essentially a burning civilization. We burn coal, we burn gas, and we burn lithium to move electrons. The reason we haven't reached the next level of energy, limitless fusion, 100% efficient batteries, or direct atmospheric carbon capture, is not a lack of imagination. It is a lack of simulation. We are entering the era of quantum simulation, the master variable that will transform energy from a scarce resource into a solved engineering problem. To understand why this is a revolutionary leap, you have to look at the classical simulation wall. Every energy process, from the way a plant turns sunlight into sugar to the way a lithium ion moves through a battery, happens at the quantum level. Electrons are not just little balls of charge. They are waves of probability. When you try to simulate these waves on a classical supercomputer, the math becomes exponentially complex. To perfectly simulate a single molecule involved in nuclear fusion or a high-efficiency catalyst, a classical computer would need more memory than there are atoms in the visible universe. Because we cannot simulate the truth of energy, we have to rely on bulk chemistry. We mix things together and hope they work. We are essentially trying to build a spaceship by throwing rocks and watching how they fall. Quantum simulation removes this barrier. A quantum computer doesn't just calculate the physics of energy, it emulates it. Because the qubits inside the computer follow the same laws of quantum mechanics as the atoms in a battery or a fusion reactor, they can provide a perfect one-to-one mapping of reality. We are talking about the ability to look inside the sun in a bottle, the plasma inside a nuclear fusion reactor. Currently, fusion is the holy grail of energy, limitless clean power. But the problem is that plasma is incredibly chaotic and unpredictable. It experiences turbulence that can melt the reactor walls in milliseconds. Classical computers are too slow to predict this turbulence. A quantum simulator could model the plasma's behavior in real time, allowing us to tune the magnetic fields to contain the star, and finally unlock a source of energy that never runs out. Beyond fusion, this technology will allow us to rewrite the rules of energy storage. Our current batteries are primitive. They are heavy, they degrade, and they rely on rare earth minerals that are difficult to mine. We know that higher density storage is possible. Biology does it every day. But the chemical search space for a perfect battery is trillions of combinations wide. Quantum simulation will turn this into a search and find mission. We will be able to architect solid-state batteries that can charge in seconds and hold 10 times more power than anything we have today. We are moving from finding better chemicals to designing them from the subatomic level up. Perhaps the most interesting application of this technology is the artificial leaf. For billions of years, plants have used a process called photosynthesis to capture energy from the sun with near 100% efficiency. They do this by exploiting a quantum property called coherence, the ability of an energy packet to explore multiple paths at once to find the fastest way to the center of a cell. We have never been able to replicate this on an industrial scale because we couldn't simulate the quantum transport of that energy. Quantum simulation will allow us to build synthetic materials that mimic this process, creating solar panels that are significantly more efficient than anything we have currently imagined. We are also looking at the solution to the carbon debt. Currently, capturing carbon from the atmosphere is so energy intensive that it is often counterproductive. We need a catalyst, a specific arrangement of atoms that can pull CO2 from the air at room temperature with minimal power. Quantum computers are the only tools capable of designing that catalyst. We are talking about the ability to turn the carbon in the sky back into high-value materials like graphene or carbon fiber, effectively turning a global liability into a global asset. The transition to a quantum energy world is the final stage of our development as a technological species. It is the shift from a world where we fight over energy to a world where we architect it. The nations that can simulate the future of power will be the ones that define the 21st century. They will be the ones with the infinite battery, the synthetic leaf, and the star in a bottle. We are no longer just looking for a better way to burn things. We are looking for a way to let the universe provide exactly what we need. The blueprint for that future is being written right now, qubit by qubit.